Okay, now let's talk about Bayesian updating. Basically, if you have taken any kind of statistics or probability course, then you have learned this in the past. But anyway, let me give you a brief review. So the first thing is that we have a so-called law of total probability as a property of probability events. So suppose we have several events y1, y2 up to yk. These events are mutually exclusive, and that means if one happens, then the others do not happen. And they are completely exhaustive. That means one of them must happen. Okay, so altogether y1, y2, y3 up to yk, they will together form a sample space, a perfect partition of a sample space. Okay, and then we say suppose x is another event. X is another event. Then the probability for x to happen is the following. We can count the conditional probability based on each yi, then x happen. For this probability, we multiply it by the probability for y to happen. So that means first y1 happens. When y1 happens, what's the probability for x to happen? Plus first y2 happen, and then given that y2 has happened, what's the probability for x to happen, and so on and so on. Summing up all of them is going to give us the whole picture of x. Okay, just one theorem, you know. Okay, for some unknowns, we have some original estimates. Okay, suppose something may or may not happen. We have a probability measurement on it. That's something called the prior belief. By having a prior belief, we will assign prior probabilities to all the possible occurrences of that event. For example, before I toss a coin, my belief of getting ahead should be 1/2. Okay, that's my prior belief before I toss a coin. Suppose my estimation is correct, then if I do an experiment by trying that particular experiment many times, the relative frequency of that event, of the occurrence of that event, should be close to my prior belief. For example, if I toss a coin for 100 times, probably I will see 48 heads, because 48 is close to 50. That counts for 1/2 of the probability. But if during my after the experiment I see 60 heads or even 90 heads, then I probably should guess or should conjecture that my prior belief is somewhat wrong. Okay, so that means I may update my belief to a posterior belief. Based on my observations, I should update my prior belief to my posterior belief. Okay, so to give you an example, let's consider popularity of a product. Suppose I have a product to sell. We don't know how popular the product is. Let's assume there are two possibilities, either popular or unpopular. Okay, and at the beginning, we are somewhat confident. We believe that the product is popular with probability 70%. Okay, suppose a consumer comes, the consumer may choose to buy it or just go away. Our estimation is that, or our understanding of this product is that if the product is popular, then the buying probability should be 60%. If the product is unpopular, the buying probability should be 20%. Okay, now suppose one guy comes and goes away. What's the posterior belief? Okay, we can update our prior belief 70% to something else. The first thing we have is the marginal probability, P and U. We believe that for probability 70% the product is popular, with probability 30% the product is unpopular. we also have those conditional probability. If the product is popular, the probability for one guy to buy it is 60%. Okay, that's how we get this 0.42. When the product is popular, the probability for one guy to buy it is 60%, and the probability for the product to be popular is 70%. So 70 times 60, we have 42% as the probability that the product is really popular and someone buys it. For this one, it's obviously 0.7 times 0.4. And for unpopular products, we have the same thing. Note that this number is pretty small because this is the probability that the product is unpopular and also the product is sold. Okay, this conditional probability is 0.2, and the probability for the product to be unpopular is 0.3. So the product is just 0.06. If at the beginning we believe the product is unpopular with a high probability, then this number is going to increase. But eventually you can see this will not be too high. Anyway, based on the current setting, we have this table. And then if we sum up across rows, we can get 48% and 52% as the overall probability for one guy to buy it or to go away. Okay, that's the marginal probability for B and G. And now, suppose we really see one consumer goes away. What's the posterior belief that the product is unpopular? It's simply the ratio of this one and this one. Okay, 28% is the probability that this product is popular and this product is sold. 52% is the probability that this product is not sold. Okay, so this is the very basic conditional probability formula, right? The probability that the product is not sold as a condition, and then we infer what's the probability for that product to be popular. It depends on these two probabilities, and then due to the calculation we can get 54%. Okay, so originally the belief of popularity is 70%. With probability 70%, we think the product is popular. But if the product is really popular, with a high probability it should get sold instead of not sold. Okay, so that's why when we see one consumer evaluating this product but then goes away, we should somewhat update our belief, and in that case we become less confident. Okay, less confident. If we try this again, show the product to another consumer and that consumer also goes away, then the updated belief on P would just become 37%. Okay, it will become even lower. Whenever one guy comes in and then goes away, the posterior belief on P will just become lower. Okay, it will always be that case. If you want to verify this, simply try to set 0.54 as the new prior belief, and the 0.46 as the new prior belief for you, and then try this again. You will see 37%. Okay, after 5 customers go away in a row, the posterior belief will directly goes down to 7%. Okay, if our product is really popular, it should not be the case that 5 consumers go away in a row. That means we now have a very strong belief that the product is really unpopular. Okay, so now we are ready to formalize the updating by the so-called Bayes theorem. Suppose we have those events y1 to yk that are mutually exclusive and completely exclusive, and x is somewhat another event. Then, in general, given the observation of x, we may update our belief of the probability for yj to occur according to this formula. Sign typos here. This should be x, this should be x, and then this should be yj. Okay, so from here to here, this is the usual theorem for conditional probability. Okay, conditional probability, and then the probability of x can be expressed by the law of total probability. Okay, that's the denominator. For the numerator, it's just another application of the definition of conditional probability. So this is how we update our belief based on an observation. When we are mapping this general formula to the previous example we gave to you, then y1, y2 are popular or unpopular, and x, your observation, is going away or buying one product. Okay, that's how this maps to our specific example. In general, in some cases, it is clear how yi's affect x, right? We sometimes know that whether a product is popular affects whether the product is sold. So when we are doing updating, we are going in the reverse direction. We use x, we use the observation to update our belief about those hidden facts, and that's Bayesian updating. Okay, so this is the formula. You may want to go over it. In the next two videos, we will tell you how may we apply Bayes theorem and Bayesian updating to study a signaling game. Thank you.